Hi, welcome to R&AC Academy. My name is Ram Prasad. Let me give a small brief about me. I did my masters in R&AC and then I worked for 25 years with the various organizations involving in product development and technology innovation functions. I had 5 patents filed on my name. Out of my passion, I transitioned into teaching. Presently, I am into coaching GATE and IES aspirants on R&AC subject. I also conduct workshop on R&AC systems, faculty development programs, etc. for the engineering colleges. Recently, I conducted webinars for the members of ISHRE and ASHRE. Coming to this program, I am presenting here with a series of lectures on refrigeration systems for the benefit of the students and professionals. I believe these lectures will be of great help and learning to all of you. Performance computations for VCR cycle. This is the 4th lecture in the series of lectures on refrigeration systems. In this lecture, I will start with pH diagram, pressure enthalpy diagram. In this, pressure will be on y-axis, specific enthalpy with the kilojoule per kg as its unit will be on the x-axis. You have a saturation dome and this pH diagram is specific to a refrigerant. On the left side of the saturation dome you have the liquid region, right side vapor region, and within the saturation dome you have liquid plus vapor region. That is, phase change happens within this saturation dome. This is the saturated liquid line, other side is saturated vapor line, both will be merging at critical point. All the horizontal lines are constant pressure lines, all the vertical lines are constant enthalpy lines. In addition to this, you need to understand and know about 3 more lines on this diagram. First one is isothermal lines, constant temperature lines. For liquids and ideal gases, enthalpy is a function of temperature only. Therefore, in the liquid region, the isothermal lines will be merging with the constant enthalpy lines, and hence these isothermal lines will be vertical lines in the liquid region. And during phase change, the pressure and the temperature of a fluid will be fixed. Therefore, in the saturation dome, the constant temperature lines will be merging with constant pressure lines and hence you will have them horizontal. And after the saturation dome, the constant temperature lines will be going down like this. As you go towards the right, the temperature increases. The next lines are isentropic lines, constant entropy lines. These are the inclined lines on the pH diagram, and as you go down, entropy value increases. The third one is the specific volume lines, constant specific volume lines, and as you go down, the specific volume of the refrigerant increases. Let us now plot a VCR cycle on pH diagram. But before that, let me define simple VCR cycle. The VCR cycle with saturated liquid at condenser exit, saturated vapor at compressor entry, and with the compression happening isentropically. When these 3 conditions are met, then that VCR cycle is called simple or standard or ideal VCR cycle. Let us now plot this simple VCR cycle on pH diagram. We have the VCR cycle operating between 2 pressure limits, that is PC and PE. The VCR cycle will be operating between condensing pressure PC and evaporating pressure PE. Let us start with the first condition. Saturated liquid at condenser exit. What is the pressure of the refrigerant at the condenser exit? That is nothing but PC. Therefore, saturated liquid state of the refrigerant corresponding to PC will be here. As this is the condenser exit and as the heat rejection inside the condenser happens isobarically at PC, then this is the process line for the condenser. Let us go to the next condition, that is saturated vapor at compressor entry. The pressure of the refrigerant at compressor entry will be P. Therefore, the saturated vapor state of the refrigerant corresponding to P will be here. So, the second point is compressor entry. And then the third condition is compression must happen isentropically. And we had seen that isentropic lines will be inclined lines on pH diagram. So, draw the isentropic line from the compressor entry until it intersects with the PC line. And that gives us the third state point. After the condenser, the refrigerant will be flowing into the expansion device. In the expansion device, the refrigerant will be expanded following constant enthalpy process. So, drop a vertical line until it intersects the PE line. That gives us the fourth state point. After the expansion device, the refrigerant will be entering into the evaporator, where the refrigerant will be absorbing heat isobarically. So, draw a horizontal line and complete the cycle. Let us number the states 1, 2, 3, 4. 1 to 2 is isentropic compression process, 2 to 3 is isobaric heat rejection process, 3 to 4 is isenthalpic expansion process, and 4 to 1 is isobaric heat absorption or producing refrigeration effect. Let us now map these four state points on the VCR system, vapor compression refrigeration system. As process 1 to 2 happens inside the compressor, so state 1 represents compressor entry and state 2 represent compressor exit or discharge. Similarly, 2 to 3 represents the condenser heat rejection happening at condenser. So, 2 is condenser in, 2 is condenser in and 3 is condenser out. Similarly, 3 to 4 is expansion device in and expansion device out, and 4 to 1 is evaporator in and evaporator out. Please note here that the state of the refrigerant at evaporator exit and compressor entry is same. It is because there is no designed process to happen inside the suction line, and hence the state of the refrigerant does not change inside the suction line. The same explanation is applicable for other state points also. Temperatures in VCR cycle. In VCR cycle, you need to know about three temperatures. First one is saturation temperature corresponding to PC, that is condensing pressure, is called condensing temperature TC, and the constant TC line on pH diagram looks like this. The second one is the saturation temperature corresponding to P is called evaporating temperature TE, and the constant TE line looks like this on pH diagram. The third temperature is the temperature of the refrigerant corresponding to state point 2, which is nothing but the discharge of the compressor, and T2 is called discharge temperature, and the constant T2 line will be looking like this. In simple VCR cycle, T2 will be always greater than TC. VCR cycle plotted on pH diagram makes the process of performance computation simpler and also makes you understand quickly about what is the data that is available with you and what is not. Let us look at that now. First, let us drop all the state points onto x-axis. So you will get H1, H2 and H3 or H4 because H1 and H3 and H4 are equal. Process 4.1 happens inside the evaporator. Therefore, the enthalpy difference between 1 and 4 is nothing but the refrigeration effect produced by the cycle. Process 1 to 2 happens in the compressor. Therefore, the enthalpy difference between 2 and 1 is nothing but the work energy supplied to the cycle. Process 2 to 3 happens inside the condenser. Therefore, the enthalpy difference between 2 and 3 is nothing but the heat rejected by the cycle. Please note here that we could clearly see HR is equal to RE plus W on this diagram graphically. If we put all these in expression format, then this is how they will be. RE is equal to H1 minus H3, W is equal to H2 minus H1 and HR is equal to H2 minus H3, all expressed in kilojoules per kg. If M is the mass flow rate of the refrigerant in kgs per second, then you will get three more terms. M into RE is the refrigeration capacity, M into HR is heating capacity, M into W is power input PN. All these three terms are expressed in kilowatts. If V1 is the specific volume of the refrigerant vapor corresponding to state point 1, then M into V1 is the actual volume of the refrigerant vapor sucked into the compressor per second, expressed in meter cube per second. We will be taking this up while discussing volumetric efficiency in subsequent lectures. Please park it aside for the time being. The last one is COP. It is expressed as RE by W or RC by power N. Both are same. Next, isentropic efficiency. What is isentropic efficiency? It is the ratio of isentropic work input to actual work input. How these two terms are different? Whenever the compression process happened isentropically, then the work input needed to the cycle would be the minimum. But whenever the compression process deviates from isentropic process, then the work input needed to that cycle would be higher. Let us understand this phenomena using pH diagram. 1, 2, 3, 4 is the baseline cycle and RE and W are corresponding to that baseline cycle. If the actual compression is deviating from the isentropic process, then what will happen to the state point 1 and 2? Please understand that the deviation from isentropic process is happening inside the compressor. Therefore, the state of the refrigerant entering into the compressor remains unchanged. However, the state of the refrigerant at the compressor exit will move towards right to the state point 2 dash. Therefore, the actual cycle would be 1, 2 dash, 3 and 4. And if you drop the state point 2 dash onto x-axis, what you get is H2 dash. And the actual work W dash is equal to H2 dash minus H1, which is greater than the isentropic work input W. Therefore, the expressions for isentropic efficiency are W divided by W dash, H2 minus H1 by H2 dash minus H1, P in divided by P in dash. With this lecture completes, and if you have any questions, doubts, etc., please feel free to write to me. The next lecture would be on engineering calculations for VCR cycle. See you then. Thank you very much.